The first thing that you typically do when you get a new data set is you create some graphs to help you understand what's happening with the data. This quote is actually really important. If you read the quote, in most of the visualizations that I see, people first decide on the result they're looking for or the stories that they're creating, and then they create a chart to show it. You would be much better off first creating the chart, finding out what the data says, and then creating your story. That's a quote from Jeremy Howard. And I think it's very important because we want to make sure that we're letting the data drive our decisions and not letting our decisions drive our presentation of the data. We always want to look at the data and see what the data are telling us before we continue to move on with our analysis. The old saying, a picture is worth 1,000 words, really applies here. So we're going to talk a little bit in this lecture about visualizing data and about some of the best practices that are associated with the visualization of statistical data in particular. When we receive a new data set, one of the first things we want to do is look at a frequency distribution. And frequency distributions apply both to categorical, so nominal and ordinal data, as well as to interval data. They'll look a little bit different in terms of how those distributions are computed, but the idea behind a frequency distribution is that the data are broken up into classes or groups or bins. You look at the frequency of observations that occur in each one of those bins, and then you display that information via a histogram for interval value data, or a bar chart or a pie chart for categorical data. By way of example, these are some data concerning typical breakfast cereals. There is a subset here on the screen that you can see, and the spreadsheet, if you'd like to take a look at it, is also posted online, so you can download this spreadsheet and play with it yourself if you'd like to. You see the name of the cereal. You have things like the manufacturer of the cereal. Those letters represent Nabisco and Quaker and Kellogg's and so forth, General Mills, all of the different typical breakfast cereal manufacturers. That is a nominal or a categorical variable. And so if we wanted to create a frequency distribution, we could display that using a bar chart or a pie chart. Something like the characteristics of the number of calories or sodium or carbs, those are interval valued data, and those will be displayed using a histogram. So here you see the manufacturer. You see in the upper left corner of the slide there the tabular frequency distribution. So we have a listing of each of the manufacturers that was present in the data set. We have the number of times, the count that each of those occurred, and we have the percentage of the total number of observations listed there as well. And so you can display this as a pie chart or a bar chart. I personally would recommend using a bar chart rather than a pie chart. I know a lot of people like pie charts. They're visually appealing and often are used in business context, but I think the histogram or the bar chart is much easier to read. It's easier to get the information directly from the bar chart. And so we'll talk in a minute about why that's important. But the idea here is that you can see the frequency of occurrence either based on the size of the pie or the height of the bar, that would allow us to see things like Kellogg's is the most frequently occurring manufacturer in this data set. American Home Food Products is the least frequently occurring. Kellogg's is in the data set much more often than something like Nabisco, for example. So it allows us to begin to understand the distribution of manufacturers within the data set. If we wanted to look at one of the characteristics of the cereal, like the number of carbohydrates in a particular serving, we could also create a frequency distribution. In this case, the data are broken up into bins, and within each of those bins we determine the number of observations. So between 2 and 5 grams of carbohydrates, on the right hand side of the screen there is 1 observation. Between 5 and 8 grams of carbs, there are 3 cereals that have that number of carbohydrates. You can see that the majority of cereals here, if you look in the middle of the distribution of these data, right around 14, that seems to be where you hit kind of the max, or what's called, we'll refer to in just a minute as the mode of the distribution. But it allows you to see that a lot of these cereals have carbs somewhere in that range of 14 to 17 carbs. We have what we would call an outlier down there at the very left hand side of the histogram. Right at 0, there's one observation there that's between 0, 0, and 1. That seems to be an unusual observation. It is possible, I guess, that there's a no-carb breakfast cereal, but it could also be possible that that observation represents a problem with the data or a miscoding, so perhaps someone actually typed that number in incorrectly. So when you see unusual observations that stand out from the rest of the distribution, like the one on the far left-hand side of this histogram, we refer to those as outliers or extreme observations, and you want to take note of those. They're going to be important for us as we begin to think about how to numerically summarize our data. They also are important for us as we begin to cleanse our data and ensure that our data are representative of what we believe is correct information. When we take a look at a histogram, we are going to be analyzing the shape of that histogram. The shape of the histogram is going to help drive some of our decisions about how we numerically analyze these data. So one of the things we're interested in is whether or not the histogram is symmetrical. Symmetry just means that if you were to put a line down the center of the distribution as represented on this screen here by the red lines, if you were to fold the distribution in half around that line, it would be a mirror image of itself. So a perfectly symmetric distribution is going to look exactly the same on either side of that line. And you can see there are a number of different ways that could happen. We often will be looking at distributions that are more similar to the one on the left, kind of bell-shaped and symmetric, but there are lots of ways that you can have a symmetric distribution. So we might want to understand, first of all, whether or not a histogram has a symmetric shape, or whether that histogram is skewed. Skewness just indicates that there is a long trailing tail that points off to one side of the graph or the other. And so in order to remember whether the distribution is skewed to the right or skewed to the left, I like to think of it as the distribution is skewed in the direction that the tail is pointing. So the first graph there that's skewed to the right, you see the data are kind of bunched up on the left-hand side of the graph, but the long tail points towards the right. So this is skewed to the right. You can think about a variable like commute time. That's a distribution that has a very naturally right-skewed distribution. Most people, when they are choosing where to live in relation to their job, try to minimize that commute time, keep it to maybe under an hour, and so you tend to see lots of commutes that are maybe between 0 and 20, 30, 40, 45 minutes, so they tend to be on that lower side of the spectrum. But there are people who live further away, either just by distance, so they live in a more remote or maybe suburban area, or live in another city or town and they commute into a job, or they live in an area where there's a lot of traffic and so their commute time is just long due to traffic. So there are people who might be commuting an hour and a half, 2 hours, 2.5 hours, and so we see those, there are less of those, they're going to trail off to the right hand side. So that's a skewed distribution. Skewed to the right has the long tail pointing to the right. On the other side of the screen, skewed to the left has the long tail pointing to the left. We also referred to skewed to the right as positively skewed, and a distribution that's skewed to the left as being negatively skewed. And then I also referred just a moment ago to the mode of a histogram. The mode is the most frequently occurring class in the histogram. This would be true for a bar chart as well. So if you see a chart or a graph, that tallest bar in the bar chart or the tallest bar in the histogram would be the mode of that distribution. There may be a single mode, which we would call a unimodal distribution. There may be multiple modes. The graph here has 2, so we would call that a bimodal distribution, but you could also have multiple modes. You could have more than 2. Most frequently you see 1 or 2, and again the mode represents the class that has the largest number of observations, or that is the most frequently occurring in the data. So those are the characteristics that we're interested in when we're taking a look at histograms. Now I'm going to shift gears just for a minute and talk a little bit about some best practices when you're generating statistical graphics. And there will be a whole course that will go into more detail on data visualization and things that you can do to build interesting and informative graphs to describe and to display your data. But I want to make just a few points here because I think it's important, again, from a statistical perspective, that we think about graphs in the right way. So graphs in that first bullet point should be used to convey complex ideas with clarity, precision, and efficiency. So in other words, if you take a look at a graph, you want to create a graph that's going to highlight some of the complexities or the intricacies of the data, but that allows you to see them very quickly and crisply and easily. There are patterns that I will never notice if I'm scanning through a column of numbers that can become very, very clear whenever I take a look at the right graph. So graphs should stand on their own. If you have to explain a graph, then it's probably not the best graph for the data. And a graph should really have a specific purpose in mind. It should be generated with the idea of conveying a particular thought. And so think about that when generating a graph. What is it that you want to understand? Is it the shape of the distribution? Is it the frequency of occurrence of a particular item of interest? What is it that you're trying to convey? Is it a relationship between two variables? And then you want to ensure that the graphs are easy to read, that you use simple colors. Light colored backgrounds are better. Dark colored backgrounds make it very difficult to read. You want legible fonts. Continuing with those same thoughts, you want to make sure that your axes are scaled and labeled appropriately and that the symbols and lines are easy to read. You want to be careful with using color to convey information because you do want to ensure that graphs that you generate are legible or understandable or interpretable to people who may have red-green color blindness. So if you were to print a graph in black and white, you want to be sure that anything that you conveyed with color also would come through in black and white. Again, for the purposes of making sure that it's accessible, as well as for the purposes of ensuring that it's printable. So not everyone will print in color. If you're printing on a black and white printer, you want that graph to still be understandable. And you want to use the simplest plot appropriate to convey the information that you have in front of you. If you're interested in learning more about this topic, there's several references that I've included here. Edward Tufte and William Cleveland are very well-known experts in the field of statistical graphics, and they have each written books on the subject, entire books on the subject. Stephen Few is a more modern consultant on the idea of graphics, and he has a website, perceptualedge.com, and he talks a lot about not only statistical graphics, but conveying data and information that is meaningful in a business context as well. So he takes it one step beyond to business graphics and how they relate to statistical graphics. So if you'd like to learn more, those are some resources that are available for you. So with that in mind, we're going to kind of continue down this side path and think about what makes a graph good or bad. In particular, I have a few bad graphs, and we're going to talk about why they're bad. Some, it might not be so obvious. Some, I think it will be pretty clear. But to give you the opportunity to also think about what makes a graph good or bad, your discussion exercise this week will have you go on a little search through the internet to find some graphs that you believe are bad and give you the opportunity to discuss what makes those graphs good and bad and what can make those graphs better. So here are a couple. These graphs people may not really look at and think those are bad graphs. They're bar charts of a sort. But the issues with these graphs, the one in the upper left-hand corner is three-dimensional. And so if you think about it, the goal is to try to determine the number of singles sold, which one, which year had the most singles sold. And if you're trying to compare 1995 to 1997, for example, you have this three-dimensional effect, you have this perception, this visual depth that is sort of going from front to back, so it's getting smaller as you go from front to back because of that 3D nature of the graph. It's difficult to determine exactly what is the top of each one of those bars. So 3D bar charts, while they look interesting, are actually really difficult to read. If these bars were closer together, it becomes almost impossible to tell exactly what is the value for each of those bars and how do they compare. The one on the bottom right is probably a little bit more obvious, and again, this is a really easy graph to create with something like Excel. But here we not only have the three-dimensional bars, we also have a multi-dimensional graph that obscures a lot of the information. So if we're reading across the candidates, you can see what's happening with Trump, but when you go to Carson, those purple bars, we can't see what the pattern or what the trend looks like across the axis that has PPP, CNN, CBS, and so forth, we can see a little bit around one row for each of the candidates, but we can't really fully understand what's happening with that graph because of the way it's been presented here. This graph is interesting and entertaining. It's looking at sales across different fast food restaurants, and the idea the person was trying to take on in this graph was to use the symbol associated with the restaurant to represent the sales. And so you see the golden arches there at $41 billion in sales. The golden arches are much, much taller than, for example, Starbucks, which had $4.1 billion in sales. But trying to compare this, how do you compare Starbucks to Taco Bell, for example, beside of each other? This is just a cluttered graph. I mean, you look at it, it's pretty clear that it's talking about fast food restaurants, but beyond that it becomes almost impossible to really read any useful information. And then the GDP of Afghanistan is back there sort of behind that graph. So it's cluttered, it's entertaining, but it's not very informative from a statistical perspective. It would be much better to have a nice, clean, simple, two-dimensional bar chart to represent these data. This is a graph that was presented by a news organization. News organizations make mistakes, so just keep that in mind whenever you are consuming graphical data. You always want to keep your thinking cap on and be looking critically at the information that's being presented to you. In this particular situation, the percentages don't add up to 100%. That could be for a number of reasons. We don't know that these percentages were mutually exclusive, so they could have had people maybe rank candidates or something like that. So they could have also, chosen Palin and Huckabee, or Huckabee and Romney, or what have you. We're not sure how this information was generated. It could be a mistake by the person who actually generated the graphic when they generated it not based on data but just rendered it visually from that perspective. But the bottom line is, if you show a pie chart and you put percentages on the pie chart, those percentages should add up to 100%. So make sure that the graph that you're using correctly conveys what's happening behind the scenes and that it's labeled properly. And then this is one of my favorite bad graphs, because if the cute little kitty was not there, this would be a great graph. This is a statistical graph. It has box plots. We're going to talk about those in the next couple of lectures. It has the data points shown. It's got a line that visually connects the box plots so you can see the trend. But whether this graph was based on pet food or something about maybe adopting pets, or whether somebody just had their screensaver in the background as their cute little kitty, I don't know exactly how the cat made it into the graph, but the cat just completely distracts from what would otherwise be a really useful statistical graph. So keep that in mind when you're creating graphs. Make sure the graph is simple, it's easy to read, it conveys the ideas, it's labeled properly, and don't become so concerned with making the graph cute or adding a lot of bells and whistles to it. Instead, make sure that the graph is clearly conveying the data at hand, and that will be both useful from a business perspective in terms of people consuming the information you're providing to them, and it also makes the graph really useful for you, as that becomes the launching pad for the rest of the statistical analysis you're going to do.